welcome to Rajashekar classes on applied data science with Python. This is lecture number 429. In this lecture we will try to understand cascading classifiers. So since we have seen bagging, boosting and stacking, these are three very popular strategies for combining or ensembling models. Fourth such very popular method is called cascading. To explain cascading, let me take a simple example. Let's assume we want to build a system that predicts whether a credit card transaction is fraudulent or not. We want to build a machine learning system which given any credit card transaction, it determines whether it is fraud or not. One way to build it is, so every time given a transaction, I represent a transaction as a vector. I can represent transaction using vector based on lot of things, isn't it? Yes, like what is credit score of a person, who is making the transaction, what is the location at which making the transaction, is it has typical location that he does a transaction. Typically, if I do a transaction in one city, suddenly if I start doing a transaction in completely different country, that's a case for concern. So credit card companies have lot of domain knowledge which they create a vector. Now, given this query vector or a query data point, I could have model M1. Let's call this as model M1. This could be any model. This could be logistic regression. This could be logistic regression model, SVM model, whatever the model. This model, let's assume, predicts probabilities. Let's assume this model M1 gives you probability. Let me assume this model gives you probability. Which model? Model M1. Let's assume class label 1 means, what is class label 1? Class label 1 means fraud. Class label 0 means not fraud. Let's just say, so if it say that the probability YQ, it gives probability of YQ equal to 0 and similarly probability of YQ equal to 1. Let me say I have a transaction. This transaction is represented in the form of a query vector XQ. I am feeding this query vector XQ to my model M1. Isn't it? My model M1, this probability of, it's giving probability of YQ equal to 0. It's giving two probabilities, probability of YQ equal to 0, probability of YQ equal to 1. 0 means what? Not fraud. 1 means what? Fraud. That is our simple notation. Model gives you probability value, isn't it? What it gives, this particular model is giving probability value. Now the probability of YQ equal to 0 is very high, which means probability, let's assume probability of YQ is very high, which means probability that he is not fraud is probability 0. Probability high means what? That probability that he is not fraud is very high. So let's assume, you can say that if probability of YQ equal to 0 is, probability of YQ equal to 0 is greater than 0.99. If you are more than 99%, just this is an example, then you are sure that it is not a fraudulent transaction. But if it is not, given a query point, let's assume the probability of yq equal 0 is less than or equal to 0.99, then I want to be really sure that whether it is not fraud, isn't it? If probability of yq is equal to probability, if this probability is less than or equal to 0.99, let's assume this model has a perfect prediction, especially when the probability score is very high. If probability score is less than 0.99, I wanted to be very careful. Why? Because if I let a fraudulent transaction through, I can lose thousands of dollars. I can lose lot of money. If I let a fraudulent transaction through, isn't it? If I allow, I can lose lot of money if I allow fraudulent transaction. It impacts my business as a credit card company. So what I do here is I train other model M2. Let me train other model M2. Just this, as usual, this transaction is represented in the form of query vector xq. I fed this particular query vector to model M1. If probability of yq equal to 0 probability means not fraudulent, is greater than 0.99 means I can declare that transaction as not fraudulent transaction. When I am not sure, in this case, I am very, what happens when I am not sure? In this case, I am very sure because my probability of yq equal 0 is greater than 0.99, is very high. So when I am very sure, I declare that is as yes. When it is not fraud. Yq equal 0 basically means not fraudulent transaction, isn't it? That's what we discussed. But even if I am slightly unsure, I would rather train other model M2, isn't it? This model again gives me a probability of yq equal to 0. This is different model, this different model M2. Remember, your M2 is different model. That's important. Your M2 is different model than M1. Let's say this probability is greater than 0.99, isn't it? Again, I will declare it is not fraud, isn't it? If probability is greater than 0.99, I can, if I am very sure, I will declare it as not fraud. Again, if it is not, I might want to keep I might want to keep training, isn't it? If it is not, what happens? If it is not, I want to keep training, isn't it? So these are called, what is this? These are called cascade of models. These are sequence of models that your XQ, your query point XQ, goes through. At every stage, we want to be only, if you are very, very sure, again these models typically go with increasing complexity. That's important. M1 complex, what does it mean? These models go through increasing complexity. There will be very, very simple model at start. Your M1 model may be very simple at starting. There will be very, very simple models at start. Very, very good at start. Very good at determining if it is not fraud. If it is not fraud, it is done. If you are not sure, that there is complex model here M2, your model M2 is complex than M1, and here you have complex model here M2, and typically more complex model here, even you can have more complex model like M3, and so on and so forth. Typically in credit card, what happens, just if you observe, just see what am I doing here, just I am checking, just let me say like this, just if you slightly unsure, just unsure is means what, if it is less than or equal to 0.9, again I am trying another model, again I am checking, if probability is again is greater than or equal to 0.99, probability of IQ is equal to 0, then I can say it is not fraudulent transaction. Even if again if I am not sure here, again I will go to another model, that is model M3, isn't it? Here model M3, and so on, so on and so forth. Typically in credit card, what happens at the end, there is often human, there is sometime human who actually calls a credit card holder and says that have you done this transaction, which is like absolutely be certain that the person, if the person has done the transaction, it actually happens a lot in credit card transactions. So they have bunch of models, but at the end they have human intervention sometimes. Let's assume there are 10 models, then let's assume there are 10 cascade of models. Let me assume here, just see here, M1 is very simple model, M2 is complex model, M3 is more complex model. Let's assume there are cascade of 10 models. At the end of these 10 models also, if they are not sure, if they are not fully sure that it is not fraud transaction, that, let me repeat, at the end of these 10 models also, if they are not fully sure that it is not fraud, they would actually have human teleoperator who would call the customer, who would call the credit card holder like me and say, Mr. Rajshekhar, have you done this transaction? Isn't it? Have you done this transaction? When I approve it, when I say yes, then it's otherwise if I say no, I have not done it, this seems to be fraud case to me, isn't it? He would declare, if I say if I say it depends, if I say no, I have not done it, this seems to be fraud case to me, and it would end, it can be declared as false transaction. This is one example of cascade model. There are many cascade models which can occur. For example, this can occur where typically used when the cost of making a mistake is high. This is important. Typically these cascading classifiers are used when the cost of making a mistake is high. For example, in credit card transaction or in medical domain. Suppose if I want to determine whether a patient has cancer or not, I would get a query point XQ. I would train model M1, isn't it? It happens these cascading classifiers are applicable generally in credit card transactions and medical domain. Let me take medical domain. If I want to determine whether a patient has cancer or not, I would get a query point XQ, isn't it? Patient has cancer or not, I would get a query point XQ. I would train a model M1, isn't it? If this model is very sure that the patient does not have cancer, it will say not cancer, isn't it? Even if it has small doubt, even if it is slightly not sure, then it would have more complex model, isn't it? More complex. M2 is more complex than M1. Even if this model M2 also says not cancer, well and good. Even if it has a small doubt, it would keep going on. Typically, at the end you have specialist, you have a doctor at the end. So typically for many of the systems typically have a human, not necessarily always. If all these models are not sure, let me look at the doctor. This is good. Instead of doctor seeing thousands of cases every day, probably 99% cases are already taken care by algorithms. Only 1% of the cases comes to doctor. So these are cascade models. Cascade models, you have to slightly careful when you train cascade models, because look at it, cascade models are like this: model M1 followed by, just see, model M1, actually at the end of this let me say model M1 followed by model M2 followed by model M3. So you train your model M1 on total training data, detrain and evaluate on test data. So now wherever you whenever you are sure, let's say class label y equals 0, wherever you are sure, you let through. Wherever you are not sure, you pass it to the next stage. So the data set you should use, the data set you should use to train M2, the data set that used to train model M1 is whole training data set, isn't it? For model M1 we are using whole training data set. The training data that used to train model M2 is little bit different from model M1. Anyway, we will try to understand how this training data can change from model to model in future classes. Time being, just assume, let me say, let's assume you train a model M1, you get a query point XQ, you train a model, let's say this probability of belongs to class 0 is P0. Probability of belongs to class 0 is, let me say, P0. P0 is the probability that YQ equals 0. If P0 is greater than 0.99, then you terminate here, say YQ equals 0. Here P0 is nothing but probability. What is this P1? P1 is probability of YQ equal to 1. Let's use this notation. Now I could say if P0 is less than or equal to 0.99, but if 0 if 0 less than or equal to 0.99, but P0 is greater than 0.9, then I could use model M2. I could use model M3 if I could use model M3 if P0 is less than or equal to 0.9. This is like if else condition. I can write entire thing in terms of if and else. From my own personal experience, I have seen cascade being built for fraudulent detection. There are so many cascading classifiers, cascading models you can find in fraud detection. Cascade models, if the cost of making mistake, cascade models are more popular if the cost of making mistake is high and you want to avoid it at any cost. This is the key reason. This is not only reason why we have to use cascade models, but in cases like these cascade models are extensively used. I have seen cascade models used to improve model performance. So there is no set limit on how cascade models should be built. Here is the simple introduction to cascade models. It's very case specific and probability specific. So cascade models, I have seen cascade have been built with 20 levels in some cases, some case studies that I have read. So I have to improve the model slowly but systematically. This happens typically when a team working on a problem for years and years, and they want slowly and systematically improve, especially for highly critical problems like medicine or in fraud detection. Imagine in the case of Visa or MasterCard, I can say in the case of Visa or MasterCard, if you let through 0.1% of transactions, if you miss 0.1% of fraud transaction, that could result in billions of dollars of loss, because Visa and MasterCard companies are world largest credit card issuers. So it's again depends on the problem, depends on the context, depends on the problems, and depend on the context and type of types of the cascades best fit. But general idea is like this: sequence of models applied like this. We will see some cascades in our case studies in our future classes. Just go through it. If you have any difficulty, please keep a comment. In my next lecture, that is in lecture number 430, we will discuss about Kaggle computation versus real world. Thank you very much.